fossilized birth death process. So we're going to get that kicked off by talking a little bit about the fossilized birth death process and what that is. So the fossilized birth death is a probabilistic model for estimating divergence times for a dated phylogeny. And this model is unique in that it treats fossil and molecular occurrences as part of the same generating process. And what this allows us to do is avoid calibration densities. I'm sure a lot of us have built phylogenetic trees using node calibrations and calibration densities, and I'm sure a lot of us know how challenging that can be because you're translating your knowledge about the fossil record and fossil occurrences into prior densities, and that's something that can be quite challenging and subjective. And fossilized birth death allows us to avoid doing that. It also allows us to use multiple fossils per node, which is something that's been challenging to do coherently with calibration densities. And so I want to walk us through the different model parameters that are in the fossilized birth death. So over here is a graphical model representation of the fossilized birth death process. In the middle here we have a time tree, which is what we're trying to estimate. And we have our 4 parameters that are the models, or the parameters that we are using to estimate that time tree. And you'll notice that these are in solid black circles. That means that these are parameters that we are estimating the value of. So here in red we have lambda. Lambda is our speciation rate, so the rate at which new lineages are added to our population of potential lineages. Here in red we have mu, which is the extinction rate. And I am feedback, and I'm not sure why. Then I go here we have psi, which is the rate at which extinct lineages and fossils are recovered along the tree. And rho, which is our extant sampling proportion, so the proportion of our extant species that we have sampled in our tree. 2 other parameters of interest that we have up here are net diversification, which is speciation minus extinction, and then turnover. Oops, I have accidentally advanced a slide, which is extinction divided by speciation. Turnover is going to be fairly important in this talk, and we're going to talk a little bit more about it in a couple of slides. Something else that's pretty cool about the fossilized birth death process is that this allows us to account for the presence of sampled lineages that have sampled descendants. So lineages in which we have both sampled an ancestor and some of its descendants. And this is also something that we're going to spend a bit of time talking about today. So some of you might be familiar with this figure. This is from Tanya Stadler's 2010 paper where she described a lot of the mathematics of the FBD process. And what we have here on the left-hand side is our complete tree, or the tree as it exists in biology. You can see on this tree we have some tips that are sampled in the present. These are our extants. Each black dot represents a sample that we have collected. And you can see that we have some samples that exist on branches, or they are 2-degree nodes, and these are sampled ancestors. As you can see, some of these have descendants that we have not sampled, and some of them have descendants that we have sampled. So if we were to reconstruct a tree from this data, what we would expect to get back, and what we would want to get back, is something that looks like this, where we have an accurate representation with this node here, for example, is an ancestor to a descendant that we have sampled. Advancing too fast. So something that has kind of come out in a lot of the empirical papers that have worked with integrating fossils more completely with molecular data divergence data analysis is, now I'm going backwards. Okay, good. So for the rest of the speakers, this is in fact the dangerous device that we thought it was. So we've noticed that in some of the empirical studies that have used these methods that more completely account for fossil data, there's this kind of observation that's popping up, which is that methods such as total evidence methods that incorporate fossilized tips seem to produce older ages than did our molecular dated phylogenies using calibration densities. And so Tracy and I got to wondering if these older ages are an inherent property of these kind of more total evidence methods, or if this is somehow related to misspecification of the models that we use. And particularly, we were wondering if this is related to not accounting for the presence of lineages that have sample descendants. So, coming back to our image from 2010, ideally we want to have this tree here on the right, in which we have sampled ancestors showing up as sampled ancestors. But a lot of the initial papers using FBD processes and initial papers using total evidence methods forced every fossil to sit on a branch. So for example, this guy would have to sit on his own branch, and so would this one, and this one. And what that means is that we're increasing the amount of speciation events that we have to have represented on the tree. And generally, these are not represented as zero-length branches, they're represented as branches that have some amount of positive length. And all of that together is going to force those nodes to appear older. So for example, we're going to, oh, that creates a hand, okay. We're going to force our speciation parameter to be quite a bit higher. That can also interfere with our other parameter estimates, such as extinction and turnover, which we'll come back to. And if this is the cause of kind of these older node ages, we would expect this to increase as we have more potential sampled ancestors in our data set. So having more sampled ancestors that we're forcing to sit on branches is going to cause us to kind of outsize our parameter estimates even further. So coming back to turnover again, I want to talk a little bit about this sampled ancestor assumption. So here we have 3 different plots. And on the y-axis, we have the proportion of fossils that are sampled ancestors, and on the x-axis, we have the fossil sampling rate, so the rate at which fossils are recovered in, along our tree. And when turnover is low, we have almost all of our fossils being sampled ancestors. When turnover is very high, what we have is more fossils, but more of them sitting on terminal lineages. So we have kind of proportionally fewer sampled ancestors. And always, we're going to increase the number of sampled ancestors that we have as we increase our fossil sampling rate. So what we wanted to do is use some simulations and kind of reanalyze an empirical data set to get a handle on this problem. So we simulated 25 extant tips with nucleotide sequence data, so those are our present day samples, and a variable number of fossil tips, and they don't have data, they have their occurrence times. And we simulated trees and fossils for different values of speciation, extinction, and paleosampling. To keep it simple for today, we're not going to address the issue of extant subsampling. And again, to keep it simple, we also used a strict molecular clock for that sequence data. And we also re-examined this bear data set from Kraus and Abella. This was the data set that Heath et al. Used in their 2014 paper on the fossilized birth-death process. And for all of our simulated and empirical data, we built trees from each data set using both sampled ancestor and non-sampled ancestor models in these 2. So those non-sampled ancestor models are really just a subset of the sampled ancestors models in which we have fixed the value of possible sampled ancestors to be 0. I guess we're going straight to results. So here on my results slides, hand again. The y-axis is always going to be millions of years ago, so these are the ages of nodes in millions of years ago. And then on the x-axis, these are just 8 nodes that we picked out of our trees, because that is what fits on a slide cleanly. So this is for high turnover, so we expect for there to be lots of fossils, but many of them not sampled ancestors, and fairly low paleosampling. We still get a pretty decent amount of fossils being sampled ancestors. And what we do see is that over here on the no sampled ancestors plots, that we do end up estimating node ages as being a little bit older than the true value, which is denoted with a blue bar. And we don't have that problem with the sampled ancestors models. And when we look at our parameter estimates, from our beast MCMC logs, sorry, I should have mentioned, these are box plots where the whole range is the range of the 95% HPD. When we look at the model estimates and the model estimates of parameters, what we end up finding is that our speciation and extinction rate, individually those parameters aren't to inflated, but they are inflated relative to each other. And what that does is it forces our turnover to be quite high, a little bit higher than it should be. And this also changes our paleo sampling parameter. So the picture is a little bit more complicated than I had initially thought it was. Who knew? But it also is a picture that makes quite a lot of sense. As we increase the amount of fossils that are sampled ancestors, let me try and get rid of this hand. Okay, we find that this kind of node age effect tends to get even more inflated where we're getting older and older ages. And again, we end up having this situation where we have really made speciation and extinction rate be quite high relative to each other, and so we're forcing that turnover parameter to be even higher. And by the time we get to having an extremely large amount of sampled ancestors, we have HPD values that don't even contain the true value for those no sampled ancestors models. And they are a little bit high on the sampled ancestors models, but not nearly to the same extent. And again, we see that kind of same thing where we're forcing a really high turnover for those nodes. When we relook at some of the empirical data, what we find is that in blue, the HPDs for the models without sampled ancestors, and in red, the HPD models, or the HPDs on the models, or on the node ages for the sampled ancestors models. Ooh, okay. And we do find that those bare trees end up, the empirical data ends up being a little bit older, but not too much. That's probably related to the fact that their phylogeny is fairly sparsely sampled in the past. All right, so what I want you to walk away from is that modeling data sets with sampled ancestors using a model that does not account for them is something that can result in these kind of inflated node ages that you might have noted in the past. And that if you're also trying to estimate any sort of model parameters, this is something that can also be a big problem for those estimates. And that this effect increases with the number of sampled ancestors. So I'm running out of time, so some quick thank yous to the Heath Lab. So my lab PI, Tracy Heath, and Michael Landis, who you might have seen speak yesterday. And then the Holder Lab, through which I'm co-appointed, Mark Holder, and my lab mates Emily J. McTavish, and Skimmer, and funding. And with that, I believe I have a moment for questions.